Chapter 1, Complex Numbers Part 2. The first part we're going to be looking at is the roots of quadratic equations. A quadratic is a polynomial whose highest power of the variable is 2. A quadratic has a form az squared plus bz plus c is equal to 0, where a is not equal to 0. The small raised numbers like the 2 in z squared are called indices or powers. So in a quadratic, the highest index is 2. That is why it's called a quadratic. The solutions of the equation are called roots. They are called roots because they are the values of the variable that make the polynomial equal to 0. For example, if we have x squared minus 9 is equal to 0, then the roots are x is equal to 3 and x is equal to minus 3, because both make the expression equal to 0. So when we plug in the value 3 into x and the value minus 3 into x, in both situations, the expression then equals to 0. So if a quadratic with real coefficients has one complex root, then the other complex root must be its conjugate. So if one root is alpha is equal to p plus qi, then the other root is beta is equal to p minus qi. This is called a conjugate pair. Why does this matter? When the coefficients are real, imaginary parts must cancel out when the factors are multiplied. That only happens if the roots come in conjugate pairs. Building the quadratic from the roots. If the roots are alpha and beta, then z minus alpha multiplied by z minus beta is equal to 0. Expanding this gives us z squared minus alpha plus beta multiplied by z plus alpha multiplied by beta is equal to 0. And here is one example where we do this. If one root is 6 plus 9i, then the other root is 6 minus 9i. Therefore, we end up with a plus beta is now 6 plus 9i, that's alpha, plus 6 minus 9i, which is beta, is equal to 12. After that, we have alpha multiplied by beta, which is equal to 6 plus 9i, multiplied by 6 minus 9i, is equal to 36 minus 9i squared, is equal to 36 plus 81, which is equal to 117. So the quadratic is z squared minus 12z plus 117 is equal to 0. The conjugate root rule for polynomials with real coefficients. The same conjugate root rule works for all polynomials with real coefficients. What that means is, if a plus bi is a root, then a minus bi is also a root. So complex roots always come in pairs when the coefficients are real. An example of a polynomial. A polynomial is an expression like p as a function of x is equal to x to the power 4 plus 3x to the power of 3 minus 2x plus 7. This is a polynomial because the powers of x are whole numbers. There are no square roots of x. There is no x in a denominator. This conjugate rule is the main tool for solving cubics and quartics when one complex root is given. So now moving on to solving cubic equations. A cubic is a polynomial whose highest index is 3. So cubic has the form a multiplied by z to the power of 3 plus b multiplied by z to the power of 2 plus c multiplied by z plus d is equal to 0, where a is not equal to 0. Indices in a cubic. The indices are the powers on the variable. So z to the power 3 has index 3, z to the power 2 has index 2, z has index 1. A constant like d has no variable. The highest index is 3, so the equation is therefore called a cubic. For real coefficients, a cubic must have either 3 real roots or 1 real root and 1 complex conjugate pair. So the usual method that we use, number 1, use the given root to find any unknown constant. Number 2, factor out the known root, and number 3, solve the remaining quadratic. So here is an example. Suppose 1 is a root of z cubed minus 7z squared plus kz minus 10 is equal to 0. We substitute z is equal to 1. So 1 minus 7 plus k minus 10 is equal to 0. K is equal to 16. The cubic becomes z cubed minus 7z squared plus 16z minus 10 is equal to 0. Since z is equal to 1 is a root, z minus 1 is a factor. So factorizing gives us z minus 1 multiplied by z squared minus 6z plus 10 is equal to 0. The reason we get this is because you can imagine z minus 1 multiplied by this quadratic would give us this expression. So one of the roots gives us a factor, and therefore we are left with a quadratic, which we then can solve as a normal quadratic equation using the quadratic formula. A is equal to 1 because we have 1z squared. B is equal to minus 6, we have minus 6z. And then C is equal to 10 because we have plus 10. And when we plug in the value into the quadratic formula, we end up with z is equal to 6 plus minus square root minus 4, all divided by 2. So z is equal to 6 plus minus 2i divided by 2. Therefore, z is equal to 3 plus minus I. So the 3 roots then become 1, and then 3 plus I, and 3 minus I. The big takeaway for cubics is that once you know one root, the cubic reduces to a quadratic. And then we solve the quadratic using the quadratic formula. So the next part that we're going to be looking at, solving quartic equations. A quartic is a polynomial whose highest index is 4. So a quartic has the form az to the power 4 plus bz to the power 3 plus cz to the power 2 plus dz plus e is equal to 0, where once again a is not equal to 0. Indices in a quartic. The indices are z to the power 4 has index 4, z to the power 3 has index 3, z to the power 2 has index 2, and z to the power 1 has index 1. The highest index is 4, so the equation is called a quartic. For real coefficients, a quartic can have 4 real roots, or 2 real roots and 1 complex conjugate pair, or 2 complex conjugate pairs. So the usual method that we use now is if one complex root is given, we write down its conjugate, form a quadratic factor from those 2 roots, and divide the quartic by that quadratic, and then solve the remaining quadratic. Here's an example. Suppose 1 plus 3i is a root of z to the power 4 plus 2z to the power 3 minus 3z squared plus 50z minus 50 is equal to 0. Because coefficients are real, 1 minus 3i is also a root. So 2 roots that we are given now is 1 plus 3i and 1 minus 3i, which are obviously a conjugate pair now. These give the quadratic factor z minus 1 plus 3i and z minus 1 minus 3i. We multiply it and we get z minus 1 minus 3i multiplied by z minus 1 plus 3i is equal to z minus 1 squared plus 9, which is then equal to z squared minus 2z plus 10. So the quartic contains the factor z squared minus 2z plus 10. The remaining factor is z squared plus 4z minus 5. Now we solve. So z squared plus 4z minus 5 is equal to 0. So therefore, z plus 5 multiplied by z minus 1 is equal to 0. So the other 2 roots are minus 5 or 1. All 4 roots are 1 plus 3i, 1 minus 3i, minus 5, and 1. The simple pattern to remember, for quadratics, if one root is complex, the other is its conjugate. For cubics, the highest index is 3. Find one root, factor that root out, solve the leftover quadratic using the quadratic formula. For quartics, the highest index is 4. If given one complex root, add its conjugate. Make a quadratic factor. Divide. Solve the second quadratic.